It says the pedal crank for a bicycle has the cross-section shown. If it is fixed to the gear at B and does not rotate while subjected to a force of 75 pounds, determine the principal stresses on the cross-section at point C. So if we look at the picture here, you can see here's the pedal, the foot's pushing down on it, and then right here is the cross-section we want to look at. And you can see the area here, and then here is that point C. And we're going to do this using Mohr's circle. All right, so first let's go ahead. We need to find our internal loadings. So let's do that. We're going to basically section this here, and then we'll look at this right side. So that'll be our first thing to do. So we want to find those internal loads. Let's just make it look like a rectangle, I guess. And we'll put 75 right here. And then we're sectioning it, you know, right here. Remember, that's where we're cutting it. So now we need to put some forces over here. So usually we would put N, V, and the bending moment M, and I just assumed those directions. Now our distances from point A over to this cut, that is going to be 4 inches. So we've got that. So now let's go ahead and find those internal loadings. N is obviously going to be 0 here because we don't have any external horizontal forces. So N is 0. If we look at the Y direction, where up is positive, we'll have V minus 75. So that internal shear there is 75 pounds. And then if I take the moment about the point right here, what we're going to get, if counterclockwise is positive, is M minus 75 times 4. Set that to 0. So M then is going to be 75 times 4, which is 300. So 300, and that'll be pound inches. Okay, so we've got our internal loads. Now what we're looking for are the principal stresses. So in order to find the principal stresses, remember what those are. Those would be the max normal stresses we could have on our plane. What we need to do are find the normal stresses at C and the shear stress at C. And then after that, we'll be able to calculate principal stresses. Now to do that, let's draw out this cross section again. Make it a little bigger. On our cross section, let's draw our neutral axis first because we're going to need that when we calculate our stresses. So here's the neutral axis. Remember that acts through the centroid of the cross-sectional area. And we also have that point C. So point C is going to be, you know, like right here. So there's that point C. And then let's label some of our distances. This length down here is going to be 0.3 inches. And then from here to here is going to be 0.4 inches. Same thing down here, since it's just like a rectangle. And this distance from here to here is going to be 0.2 inches. All right. And we know that from right there. Okay, so that's our cross-sectional area that we're going to need. I'm going to go ahead, let's calculate the area of this just so we have it. So the cross-sectional area will be 0.3, that's inches, times 0.8 inches. And that's going to be 0.24. And as I was calculating that, I realized we're not really going to need that because N is 0. But anyways, we got it there already. Now let's do the moment of inertia. So we want the moment of inertia about that neutral axis. So that's going to be like an IX in the inertia tables. So 1/12 base times height cubed. So we'll have 1/12 times 0.3 inches times 0.8 inches cubed. Let's calculate that. And that gives us 0.0128 inches to the 4th. All right, so there's our I, and then we'll come back in a minute and find Q that we need for the shear. But let's go ahead and find our normal stress first and see what we get with that. Whoops. All right, so we're going to be finding normal stress. So we want to look up here and look at these internal loadings, see what would cause a normal stress. All right, usually we would have N, but ours is 0, so that won't be there. And we have M, that bending moment. That bending moment causes bending stress, which is a tensile or compressive stress, so that is like a normal stress. So we need to include that. And if you remember, the stress created by an internal moment like that is going to be my over I. So we're going to put my over I. Let's put in our values, and then we'll figure out if it's positive or negative. So we're going to have 300 pound-inches. And then I need Y. Remember what Y is. Y is going to be the distance from the neutral axis to our point of interest. So that is this value right there. All right, so obviously that's 0.2. So let's put that in here, and that is in inches. And then we want to divide by our moment of inertia, which we already calculated, 0.0128 inches to the fourth. Now we need to see if it's positive or negative. So remember, if it's a tensile stress, it's going to be positive. If it's a compressive stress at the point, it will be negative. So we need to look at our diagram here and then look at what we got. So I assumed it was counterclockwise. I got a positive number, so that means it is counterclockwise. So if we say point C is right here, right where that red dot is, and we do the right-hand rule, well, our hand is going to go in this direction, right? So if it goes in this direction, we're pulling away from point C. So that means that this is going to be a positive normal stress. So we'll put positive there because it's pulling away, making a tensile. Okay, so we've got that. And then let's go ahead and calculate this value. So that gives us a positive 4,687.5, and that is going to be PSI, or pounds per square inch. If you want, you can write that in KSI, just divide by 1,000, you'll get 4.687 KSI. So that'll be our normal stress, and let's put a little C here, because that's at point C. Now we need to do our shear stress at point C. So let's do that. And our equation that we're going to use is just that shear formula, so VQ over IT. Now V we have from right here, that's just your internal shear, 75. And then Q, we need to find that. So let's find Q, and then we can plug everything in. So for Q, what we need to do is basically take this area here and use that one to calculate Q. Right? And again, if you don't remember finding Q, if you look at the transverse shear section in your textbook, you will hopefully be reminded. So remember, we're going to do y bar prime times a prime. Y bar prime is basically the centroid of this shaded region that I just pointed out. So if we put a little rectangle here and make it shaded, we're going to go to the centroid of this, and I want to find this distance from the neutral axis. So this will be y bar prime. Okay. Now it's right in the center here of this pink region, and if this is 0.2 and this total thing is 0.4, then this length here is 0.2. So this would be 0.1 above. So we would have 0.2 plus 0.1, or 0.3. All right, so that would be what we would use for y bar prime. So we got the 0.3, that's inches. And then I need a prime. Well, a prime is just this pink region here. So we need to find that area. So again, that's going to be 0.2 times the 0.3. Right, so here's the 0.3 here, and then this distance we already said was 0.2. So let's calculate that. So we get 0.2 times 0.3. And that gives us 0.018 inches cubed. So that's going to be my Q value that we're going to use over here for shear stress. So let's start filling in these values. We've got, oops, I was going to write a 4. We've got a shear of 75, that's pounds. Q is 0.018 cubic inches. And then we're going to put that over I, which we just calculated. And then T. Now remember, the easiest way to calculate T is you have your neutral axis drawn right here. T is just going to be the amount of the material that the neutral axis comes in contact with. So for this, it's going to be this thickness or this width right here. So 0.3. All right, so that'll be our T. So we'll put 0.3 inches. And now we got to calculate that. And that value will be 351.56. So 351.56, and that is PSI. All right, so there you have it. If you want to do KSI, you can divide by 1,000 and get 0.352, I guess. I'll round it up there and make that KSI. Okay, so now we have our normal stress, we have our shear stress. This is a shear stress at C. So now we can put these on just an element, and then we can use that to get our principal stresses. Now let's draw our element here. So this is going to be our element at C. Let's just draw a little. Now on this element, we need to label our stresses. So we know we have our normal stress here. It's 4.687. We already said it's positive. So to use the same setup that we always use, at least in the Hibbeler book, to come up with our sigma x, sigma y, and tau xy, I need to put that normal stress going out like this, and this would be 4.687 KSI. We'd have another one on this side, and remember that's like our x-axis there. And then for shear stress, we have to figure out if it's positive or negative, right? So the way I always do it is, you can see I already have this little box drawn here. I just imagine we slide this element in, and this side where we cut it on that face is going to be equivalent to this side right here, because that's where the normal stress would be acting. And if we look on that face, shear is going up, it's positive, so this is the correct direction. So that means over here on this face, this would be going up for shear, and then that'll help us kind of figure out where we should be for shear. So we'd have that, and then it comes together here. That indicates positive shear, and we got 0.352. Whoops, I was going to put PSI, but it's KSI. KSI, and then we can finish out the other arrows here for the shear stress. All right, so we've got that. And remember, this right here is like the y-axis. And for positive shear, remember if they come together here, the arrows come together and form that plus sign in this quadrant, it's positive. Okay, so let's go ahead and write out our sigma x. And sigma x is going to be the normal stress in the x direction, which is this value here. It's going outward, so it's going to be positive, so 4.687 KSI. Sigma y would be any normal stress that we have in the y direction. Well, we can look here. I don't have anything, right? So that's 0. And then our shear stress, we look in this quadrant right here. Again, if they come together, like I said, form that plus, it's a positive. So we're going to have a positive 0.352. And then that's KSI. And I'm out of room. Now with these values, we can go ahead and construct our Mohr's circle. First thing we're going to do, let's find the center point of the circle. And remember, that is going to be located at the average stress and then at 0. So let's find our average stress. So that one we just do sigma x plus sigma y over 2. So that's basically going to be 4.687 over 2. And remember, that's KSI. The value there is 2.343. That's KSI. So we've got that. So the center of our circle will be located at the average stress and 0. So we already have our C coordinate here. So it'll just be 2.343 and 0. And now we want to find our point of interest, right? So I need to look at the stresses at point C so that we can figure out what our principal stresses are for this problem. So let's go ahead and write out the coordinates for point A. We'll call it point A. All right, because remember, C is the notation we use for the origin of the circle. So let's call this one, this reference point, point A. And let's put it over here. So point A is basically going to be at sigma C and then that shear stress at point C. Okay, so if we write those values out, our reference point is going to be 4.687 and then 0.352, and those are KSI values. One more thing to do before we can construct our circle, we need to know the radius of the circle, right? So remember, the radius is that capital R in, let's write out the equation here. It's going to be the square root of sigma x minus sigma y over 2 squared plus tau xy squared. We just need to plug in our values here and get our radius. Right, so if we do that, sigma x is going to be 4.687. Sigma y is 0, so I'm going to leave that off. Divide by 2, square that, and then plus 0.352 squared. Now that gives us a value of approximately 2.37. All right, so in units there's KSI. Now with those things we can construct our circle. So let me draw the circle and then we'll come back and we'll go over the points. Okay, so I went ahead and drew a circle and then put these axes on here. Now remember, this one over here is sigma, units here would be KSI, and this down here is our positive shear stress axis, or tau. That's also in KSI. So now let's go ahead and label our points. So we're going to have C, which is going to be right in the center of the circle, so right here. So if we look at that distance, we already know that it's going to be basically the average shear stress, or not shear stress, average normal stress, right? So to get to C, we need to have 2.343. Okay, so let's go ahead and draw that on here. So we're going to go from here over to here. It's 2.343. So we've got that. All right, now if you notice, this axis here, you know, cuts into the circle, right? We have this piece over here. And the reason for that is this radius. Notice the radius is 2.37, right? So that means from the center C out to the edge, it's 2.37, whereas this value is only 2.343. So that's why it's drawn that way, okay? So just so everybody is aware. All right, now we got C plotted here. Next, let's do point A. So point A needs to have a sigma value of 4.687 and a tau value of positive 0.352. So if I put that on here, let's do it in red, then we're going to be like right here. And then if we label these distances, or these points, this right here is going to be the 0.352, right? Because that's that shear value, shear stress. And then I need to have this value here. So that value in that, sigma direction, let's put this down here. This is going to be the 4.687 value from right here. Okay, so now we've got that, and then I can connect these lines. So C over to A, let's call it A there, and then this line here, line AC, is the radius value. So the length there is going to be 2.37. Okay, so we've got that. And then next thing we want to do is let's draw this angle on here. So this angle I don't know where, let me see. It's a bad place to draw that. Whoops. We'll just put it in here, I guess. This is 2 theta P1. Okay, that's what it is. So that's the orientation angle multiplied by 2 that's associated with the principal stresses. All right, so now how in the world do we find principal stress? So we've got this circle drawn. So this is our Mohr circle, it's completed, but I want to find the principal stresses. Well, remember the principal stresses are going to be located on the sigma axis at the edges of the circle. So that being said, let's see, I'm trying to find a good color here. We're going to have a point here and a point here. All right, so let's call this B. This one will be point D. So these 2 points are where we have our principal stress values. So basically we just need to figure out the sigma value for the coordinates of these points. And that's what we need. All right, so let's put that the principal stresses are given at points B and D. All right, so let's go ahead and calculate that. Now, what we need to do, remember this is the origin of our frame. We're measuring everything from this point here, not C. We want everything to be measured from here. So I need to find this value right here to get to B. So if we look at B, that means I need this distance, which is 2.343, plus this distance, right? So this distance from C to B, that's the radius of the circle, right? So I'm going to have the radius of the circle, which is 2.37, plus this distance, which is the 2.343. And that's going to give me my sigma 1. All right, so we got 2.343 plus 2.37. All right, and then let's calculate that one. And we get 4.71, and that's KSI. So this is one of our answers. Okay, that was supposed to make a box. Let's try it again. There we go. And then sigma 2, well, we're going to go to point D. All right, so this is point B. And then this one here for sigma 2 will be point D. So now, remember, we got to measure from here, measure from the origin, not C. So a lot of people always want to measure from C. We don't want to do that. We're going to measure from here and go over. So how could we find this distance? It's going to be a small distance, right? Small value. Well, if this from C to D is the radius, and I know that this length here is 2.343, then it makes sense that this will just be the radius minus this. So that's what we're going to use. Okay. So we can do, let's just do the 2.343 minus the 2.37. And we need it to be a negative number, right? Because I'm over here in this negative axis for sigma. So if we do it like this, we'll get a negative. All right, so let's subtract those. And we get negative 0.027 KSI. So that'll be our other principal stress, and this one was again at point D. So basically that is how we go about finding those principal stresses. And if we wanted, the problem doesn't ask, but if we wanted this orientation angle, this theta P1, basically we could draw out the right triangle, because if you see here, we've got this right triangle. And then we could calculate 2 theta P1 divide by 2 and get theta P1. All right, so that's how you would go about finding that. I'm not going to write it on here because it didn't really ask for it, but that's how we could find that. So the key here for the Mohr's circle, we want to get our stress values right here. So put them on an element like this, use that standard XY frame, pull out those values. Then we're going to calculate our coordinates for C, which will be the average stress, and then 0 because I want that to lie on the sigma axis. And then if we're looking for a certain point like we did here, we're going to come up with our reference point A. So that'll just be your normal stress and shear stress at that point. In our case, it was point C. So we'll get those values, come up with our radius, and then you're just going to basically plot all these on a circle. Okay, and then you can come up with your values. B and D will be the points that you use to get the principal stress values. All right, hopefully that makes sense. Hopefully you like that one. I will see y'all next time for another example.